Hey everybody, thanks for tuning in. My name is Dr. Nick Dowdy. I'm a postdoctoral research fellow at the Milwaukee Public Museum. And I wanted to record the presentation that I gave at the International Society for Behavioral Ecology in 2018 for people who couldn't make it to the talk or who couldn't make it to the meeting. And my talk today is called Behavioral and Chemoecology on the Pin, Utilizing Museum Collections to Better Understand the Bat-Moth Arms Race. And today I'm going to be talking to you about some work that I started in my PhD and that I'm continuing to work on under an NSF postdoctoral fellowship starting next month, September of 2018. And it's related to utilizing museum collections to better understand the bat-moth evolutionary arms race. And with this talk, I'm kind of hoping to not only tell you a little bit about what I'm doing, but hopefully also inspire some of you to utilize museum specimens in your own research. But I'm going to exclusively be talking about tiger moths, so I'll give you a little bit of background on these really pretty cool animals. Tiger moths are a subfamily of moths known as the Arctiinae, and there are more than 11,000 species of these moths. And to give you a little bit of context, that's about 1,000 more species than all birds or all reptiles, or it's roughly equivalent to twice as many species as all mammals or all amphibians. We've got a worldwide distribution, diverse phenotypes, and what I'm mainly going to be focused on is their capability to produce ultrasound in response to bat echolocation. And there are two organs which allow them to execute this behavior. The first is the tympana, or the ear of the moth, and this allows these insects to detect the ultrasonic cries of bats. The second is a sound-producing organ called the tymbal organ. And that's basically a blistering of exoskeleton with an air cavity behind it and musculature which will deform the surface of the organ. In addition, there are corrugations along the anterior edge of the organ. And as these corrugations buckle, they produce individual clicks, and you can see that organ in the top left part of the screen. And there are two main anti-bat functions for these clicks. The first is acoustic episematism, we also call these warning sounds, as well as acoustic mimicry. Then the second is sonar jamming or sonar interference, and these are sounds which are capable of disrupting bat echolocation. So I'm going to show you a video here. This is a sort of control interaction where the moth has no sound producing capabilities. You're going to hear chirping sounds. Those are bat echolocation cries that have been slowed down so that we can actually hear what's going on. Okay, so you notice that as the bat approached, it reached out its arm, grabbed the moth, and transferred it to its tail membrane, and then began feeding on the moth. Now let's contrast that with an example of acoustic episematism. Here on the left we have the tymbal organ of Cycnia tenera, just to show you how the tymbal organ functions and what it sounds like. So let's give that a play. So you can see those muscles contracting and deforming the surface of the organ and those corrugations producing clicking sounds. Now on the right, this is a video of a tethered interaction with an eastern red bat in the laboratory. And again, you'll hear those chirp-like bat cries, but now you'll also hear a raspy kind of sound, and those are the moth clicks. And I'd really like it if you could pay attention to the bat's flight behavior here. Okay, so what that was, we often call that turn-away behavior, or we also say that the bat aborted its attack. We see this often when a bat is presented with acoustic episematic signals. Now take this and compare it with a sonar jamming scenario. So here we've got the tymbal organ of Bertholdia trigona, a moth known to be capable of jamming bat sonar. And hopefully you can already notice that the tymbal has many more corrugations on the surface of the organ, and consequently it produces a lot more sound per unit time. On the right, this is a free-flying interaction with Bertholdia trigona and a bat predator. Okay, you can see that the bat did not exhibit any turn-away behavior, and it didn't abort its attack. It actually attempted to complete the attack. However, it was off target slightly. That's basically how sonar jamming appears to function. It seems to introduce ranging interference into the bat echolocation system. And under this NSF grant, well, I just want to quickly say, if there are any graduate students in the audience interested in potentially also applying for this fellowship, please feel free to contact me for advice. But the major questions that I want to answer in my proposal are, did sonar jamming evolve once or many times independently? What's the ancestral function of complex anti-bat signals? Is complex signaling associated with subsequent loss of defensive chemistry? And what's driving the evolution of complex sound production? Well, before I can answer those questions, I really need to lay the foundations on the components that are necessary for reconstructing the evolution of anti-bat defenses. So first, we need to be able to broadly characterize acoustic and chemical traits. Second, we need to classify those defensive strategies based on those traits. And finally, we need to generate a robust phylogeny, something that has hitherto eluded systematists in the tiger moth system. First, we know variation in timbal organ morphology exists, and we know that variation in acoustic characteristics exists, but what we don't understand is how that variation in morphology gives rise to the variation in acoustic characteristics. In order to address this, I went down to the eastern slopes of the Andes and recorded sounds from 70 species of tiger moth, preserved them, and brought them back to the United States for morphometric analyses. Today, I'm going to focus on measurements of the number of corrugations on the surface of the organ. You can see that here in figure D, and also the click rates that were ultimately produced by the organs that I measured. I also recorded the clade to which these individuals belong. Since I didn't have a phylogeny, I needed to use something to account for phylogenetic dependence between species, and so this was sort of the best method available in the absence of a phylogeny. And the result was that, yes, if you measure the number of corrugations on the surface of the organ, while accounting for the subgroup that the species belongs to, you can robustly predict the click rate for that individual with this predictive model. And so this means that now we can go into collections and examine the morphology, plug it into, we'll measure a few things from it, plug it into this model, and then get an idea of what it sounded like. Next, can we characterize palatability from preserved specimens? On the left, I'm presenting a palatable silent moth, and on the right, I'm presenting the same bat with a toxic tiger moth. And you can see that the one on the left is already chowing down, and the one on the right is doing everything it can to escape my evil grasp here. This unpalatability is often derived from pyrrolizidine alkaloids in tiger moths. These are compounds that are sequestered from host plants, sometimes in the adult stage, sometimes in the larval stage, and sometimes in both. And here again, the answer is yes. I was able to utilize an HPLC MSMS system to characterize chemical traits from tissues of preserved specimens. To accomplish this, I first had to develop a custom pyrrolizidine alkaloid and pyrrolizidine alkaloid derivative database, which is composed of more than 40,000 compounds, and also a custom fragmentary ion analysis pipeline, which will analyze the data from the HPLC. Currently, this script is written in MATLAB code, but someday I'll get around to porting it over to Python. And ultimately, what you get out of this data is not only pyrrolizidine alkaloid presence or absence, but also the identity of those compounds as well as their concentration. Although there are some caveats with concentration, although I don't have time to get into it right now, there's also a study which shows that it's possible to recover these types of compounds from dry pin specimens collected more than 30 years before the chemical analysis. Next, we need to be able to classify those defensive strategies once we've estimated what the moths sound like and potentially what they taste like. So if you've got these two signals here, how do you define when a signal is jamming or when it's aposematic? Some forthcoming experiments with naive bats and manipulated click grades show that there's no reduction in bat capture efficiency. In other words, there's no jamming effect below about 750 clicks per second. But preliminary data also suggests that not all jamming signals are equally effective. So above this jamming threshold, if a moth were to produce more sound per unit time, they may more effectively reduce their likelihood of being captured by a bat. So in order to address the phylogeny issue, we've developed a new ultra-conserved phylogenomic probe set. And this is a set of more than 750 loci. And it's really given us great results. They're very robust results, strong branch supports at the majority of nodes. And in this is the tree from the article that we're working on, and all the unlabeled nodes that are filled with black, those have 100% bootstrap support under two different tree building methods. And so layering my preliminary behavioral data on top of this phylogeny, it looks like we have evidence for at least 5 to 6 independent origins of sonar jamming, and it looks like most likely those have arisen from an aposematic ancestral function. And we have a lot more museum data to unlock, and I'm really looking forward to starting this project next month. And with that, I'd like to thank you for listening. I'd like to thank my mentors, Bill Connor and Jen Zaspel, as well as my collaborators and assistants. In particular, I want to thank Jahami Fernandez, who is spearheading the experiments on the jamming threshold with Bill Connor. And I also want to thank all the museums who have graciously opened up their doors and allowed me to execute this work. And of course the NSF, who funded not only the preliminary work, but also the upcoming phase. Thanks.